Hello friends, now we are going to discuss examples of continuous wave modulation theory, that is amplitude modulation. First we discuss superheterodyne receiver, that is used in all radio and TV receiver. Then we discuss about TV signals, and at last we discuss about frequency division multiplexing. So our first topic is superheterodyne receiver or superhet. Superheterodyne receiver is used in all radio and TV receiver as it performs an additional function such as carrier frequency tuning, filtering and amplifications. So these are the additional function beside detection of signals which makes the superheterodyne receiver common for all radio and TV receivers. In carrier frequency tuning function, the desired signal, that is modulating signal, is selected by tuning of the carrier frequency. Second is filtering function. In this, the desired signal gets separated from other modulating signal that may be picked up along the way of transmission channel. And the third function is amplification, that is used to compensate the signal power that is lost during the transmission of signals. Now we discuss the basic elements of superheterodyne AM radio receiver. The word heterodyne means mixing of signal frequencies to produce a new frequency, that is called intermediate frequency or IF. In AM radio receiver, the basic elements are receiving antenna that receive radio frequency denoted by F suffix RF that correspond to the AM signal. This radio frequency is passed to the RF section for amplification purpose. This RF section having a common tuning with respect to local oscillator that generates the locally generated frequency F suffix LO. The output of RF section and the local oscillator frequency is given to the mixture. Here the frequency of the local oscillator is adjusted high with respect to radio frequency, hence called a superheterodyne receiver. Now we discuss the first part of the superheterodyne receiver, that is called a first detector. It composed of mixture and local oscillator. The local oscillator having a common tuning with respect to the carrier frequency of the modulated signal or AM signal. One of the input of the mixture is the amplified radio frequency, that is FRF. Another input is the local oscillator frequency that is adjustable as keeping high always with respect to the input radio frequency. The output of the mixture is sum and difference of the input frequencies, that is FRF and FLO, and this provides a superheterodyne function. But for a proper tuned circuit, the difference of the two frequencies is selected, that is FLO minus FRF, and this is called intermediate frequency, that is F suffix IF. Here the difference is FLO minus FRF because for proper tuning of a superheterodyne, the local oscillator frequency, that is FLO, is adjusted high with respect to radio frequency, that is FRF. Or we can say that FLO is greater than FRF for proper tuned superheterodyne receiver. And for commercial AM radio receiver, this intermediate frequency is predefined fixed value of 455 kHz. This predefined fixed intermediate frequency is applied to the IF section, that is called intermediate frequency section. Here the IF section consists of one or more stages of tuned amplification and provides the selectivity in the receiver. So the received AM signal with carrier frequency omega c get converted into the signal with predefined fixed intermediate frequency called omega suffix if, and it is given as within bracket AC plus MT into cos omega if function of t. This output of if section with omega suffix if is applied to the demodulator, that is called coherent or synchronous detector, that is used for the recovery of the desired signal called modulating signal. So there is an advantage of using superheterodyne receiver. In superheterodyne receiver, all the incoming radio frequency carrier having range between 0.535 to 1.605 MHz get converted into fixed intermediate frequency of 455 kHz in case of AM radio. And as a result, all the successive stages are operate on this fixed intermediate frequency, so that the designing of the circuitry become very simple, and this will improve the performance of the receiver. Next, we are going to discuss the constituent stages of superheterodyne receiver in detail. In a first stage, there is RF amplifier. This is basically a class C tuned voltage amplifier. The main function of RF amplifier is rejection of image signal or image frequency, that is F suffix is. So in superheterodyne receiver, there is a problem of image signal or image frequency, and this can be rejected with the help of RF amplifier. As we know that intermediate frequency is equals to local oscillator frequency minus radio frequency. Also we know that the local oscillator frequency is adjusted high compared to the radio frequency for the proper tuning of the superheterodyne receiver. Or we can say that the desired frequency, that is radio frequency, is below the local oscillator frequency by the amount of intermediate frequency. So the purpose of the RF amplifier in the first stage of superheterodyne receiver is the rejection of image frequency. So what is called an image frequency? Denoted by F suffix is. Here is is called image signal. Image signal is a signal whose frequency is above the local oscillator frequency by the same amount of intermediate frequency. And the formula of image signal is FIS equals to FLO plus FIF. Here the image signal is above the local oscillator frequency by the amount of intermediate frequency. Now, in place of local oscillator frequency, we can write radio frequency plus intermediate frequency, that is for AM radio. And the image signal is equals to radio frequency plus twice of intermediate frequency. So we can say that the image signal is twice of intermediate frequency more than radio frequency, and this image signal is intercepted by the receiving antenna and reaches the mixture. Now the image signal and radio frequency are shown in figure. Here the maxima point is for local oscillator frequency. Above the local oscillator frequency there is an image signal, and below the local oscillator frequency there is a radio frequency. We know that in the case of superheterodyne receiver, the local oscillator frequency is adjusted high compared to radio frequency, or we can say that the local oscillator frequency is greater than FLO minus FIF. That is called radio frequency. And the difference between image signal and radio frequency is twice of intermediate frequency. And accordingly, the image signal, that is FIS, is equals to local oscillator frequency plus intermediate frequency. Also we can write image signal frequency is equals to radio frequency plus twice of intermediate frequency. And this image signal is undesirable as it cannot be distinguished by the IF amplifier, and it will be treated in the same manner as desired signal, that is radio frequency. Now we discuss this image signal with the help of an example. Here we take a local oscillator frequency equals to 21 MHz. And let us consider a desired station having a radio frequency FRF1 equals to 20 MHz, which should be received without any distortion. Now, due to some situation, the undesired station of radio frequency FRF2 equals to 22 MHz is also intercepted by the receiving antenna. And due to this, there creates a problem of image signal. So, in a first stage, the intermediate frequency is equals to local oscillator frequency, that is 21 MHz, minus radio frequency, that is 20 MHz, and it is equals to 1 MHz. And for the second situation, that is for undesired station, the intermediate frequency is also equals to 1 MHz. As we know that the intermediate frequency is the difference of the two input signals, that is 22 minus 21, that is 1 MHz. So in this situation, the intermediate frequency amplifier is unable to distinguish intermediate frequency of desired and undesired station and treat the undesired signal as image signal, that is equals to 22 MHz. And in order to remove or reject the image signal, we use a single tuned circuit before the IF stage and is given by the parameter called image signal rejection, denoted by alpha, and it is equals to under root of 1 plus q square into rho square. Here q is the quality factor of a tuned circuit and its value is omega naught upon delta omega. And in terms of frequency, it is equals to ratio of f naught upon delta f or f naught upon bandwidth. And rho is equals to image signal upon radio frequency minus radio frequency upon image signal. Next example of continuous wave modulation is TV signals. In commercial TV, the VSB modulation plays an important role, as the video signals contain significant low frequency and considerably large bandwidth. The VSB modulation technique is used in such cases. And for the effective detection of VSB wave, the circuit used for demodulation should be simple and inexpensive at the receiver side. So the envelope detection is used, which requires VSB modulated wave in addition to the carrier as input. Now we discuss the amplitude spectrum of a transmitted TV signal, that is ideal one, and is shown in figure A. And the amplitude response of VSB shaping filter in the receiver side is shown in figure B. As we know that for TV transmitted signals, the VSB shaping filter is used for the detection purpose because the TV signals are wideband signals and contain significant low frequencies. Here we note a point. Ideally, we use 55.25 MHz as picture carrier frequency and 59.75 MHz as sound carrier frequency. That is used ideally in TV signals and shown in figure A. And the information content of TV signals lies in a baseband spectrum that extends from 1.25 MHz below the picture carrier to 4.5 MHz above the picture carrier. Next, we note some points. For the demodulation of TV signals, envelope detection is used, that having VSB and carrier as input signals, and this produces a recovered video signals at the detector output. For this, we require a specially designed VSB sideband shaping filter. The detailed designing of VSB sideband shaping filter is already discussed in last video lectures. But there is a waveform distortion that is produced by the quadrature component of VSB modulated wave. And in order to reduce the extent of waveform distortion, the percentage modulation and width of the VSB must be minimized.